tools that were developed. As you can see on my screen here, we have our PMP domain, which encompasses North Carolina and surrounding areas around it. And what we did is we broke the state into 4 separate regions. So we have a series of storms, and each one of those storms is considered transpositionable to one of these zones. It may go to multiple zones or maybe only one zone, but you can see that it's broken up into 4 different regions. So the storms are going to all these different areas. And this data is all contained in the PMP evaluation tool folder. So when you download the tool, there will be some PDF documentation that goes along with it, and we'll look at that. And then there will also be a PMP evaluation tool folder. So if we look inside of that folder, we'll see we have a series of folders in that as well. One for the input, output, which can be anywhere. This is just there as a blank container right now, but you could change that. You could move it to another spot. It's just an empty box to store the output. And then our script folder. So if we look at these here, sorry about that. If we look inside of those, we can see we have a series of, in the input folder, we have a series of geodatabases. And in the first one is called AEP, and that's our precipitation frequency raster files. And we can see that we have a 6-hour and then a 24, and then a series of return frequencies. So that's all in there in this toolbox or in this geodatabase. If you want to look at that, you don't need to know about all the details of this to run the tool, but this information is all here if you did want to look at that. The next one down is our depth area duration tables for each one of the storms. So you can see here we have a series of geodatabase tables corresponding to each one of our storms on our storm list. The storm list is in here as well. We'll look at that. But if we look at these tables here, we can see that we have our precipitation for this storm as it occurred through space by different area sizes, and then also our hourly durations. So if you wanted to look at the in-place observed rainfall for each storm, this is where you can find that information. Next, going down the list, we got our non-storm data geodatabase, and this just has our grid points. So we broke this whole domain down into a series of grids, and then PMP is run at each one of these grid points. So if you wanted to see what those grid points were, and then the vector, this is actually the grid network, and this is the centroids of those. You can look at that. Here we have our storm list. We just real quick look at the storm list. We can see here we had our SPOS number representing those DAD tables. So that SPOS number, actually the storm name, the storm center location, and the date, and what transposition zones it's applied to and what type of storm it is. So that's all in there for reference. We have our transposition zones and then the actual PMP domain. So PMP can be calculated for any location, any basin within, obviously it has to be within this domain, but as long as it's in there, any area size, any basin can be calculated. And then we just have our tables for our temporal distributions, which will be applied in the tool, which we'll see later. Going on down the list, we have our adjustment factors for each storm. It's separated by storm types. We have a general storm type, a local storm type, and then a tropical. If we look at that again, we'll see our SPOS numbers representing each storm. And that just is the adjustment factors for each storm, representing the GTF and the total adjustment factor for each one of those storms at each one of the grid point locations. So if you did want to go back and see how is this storm being adjusted at this grid point, that's where you find that information. So the tools package, like we said, in an Esri toolbox. If you're familiar running any of the Esri tools, this is going to be very familiar the same way. So we can just add a tool box like we normally would, just navigate to our PMP evaluation tool folder that we downloaded earlier, and then the script folder, and then we'll see our North Carolina tools toolbox. If we add that, and we open it up, we can see we have two tools in there. So we have one for our gridded PMP calculation tool, and then we have another one for calculating the annual exceedance probabilities. So if we open this up, it's recommended to run the PMP first, obviously. So if we open it up, it looks very similar to any other tool, and it just has some input parameters that we'll need to define. Firstly is just our input basin shapefile or feature class. And this should represent an area, because what the tool will do is go in and find that basin, and then it will calculate the area size of the basin for calculating the PMP. So we'll want to we'll just do a sample basin here. We'll add that. And then we just have our next option is for the output. We talked about that earlier. You can use this output folder that's already in there, create a new one, whatever you want to do. We'll just throw it there for temporary purposes right now. Moving on, we have our different storm types here, and then we have our durations that we want to calculate the PMP for specifically. And if we look at this, we can do a drop down, and we have 1 through 24 hours for our local storm. So we can either select these individually or select them all, and we just add. So what we're telling the tool here is for local storms, we want to run the tool at 1 hour, 2 hour, 3 hours, all the way out through 24 hours. Same goes for the general storms and then tropical storms. And then going on, by default, this next one's checked. I just talked about this. So what this does is the tool will calculate the area size of the basin and then go into those DAD tables that we previously looked at and find that area size and get the rainfall specifically for this basin at this basin area size. That's the default. You can uncheck this if you wanted to, and then you can override that to make the tool use any area size. Say maybe you wanted to calculate point values for this basin as well for some reason, you could override that and run it for 1 square mile instead of the calculated area size. For this demonstration, we'll use the actual area size of the basin. The next option down is checked by default as well. And what this does is just, you can see that the basin intersects some of these grids here. So all this does is it just, if the grid is on a boundary of the basin, it just calculates when it calculates the basin average values of PMP, the average of all of the grid points, it will use these ones on the periphery as a weighted average. So they won't be as weighted in the average as something that's completely inside. So there's usually not a lot of difference, but there is a little bit. That's something that can be turned off if needed, but like I said, it doesn't usually make much of a difference. Going on, we have a option to include sub-basin averages. So if this was a very large basin and had a series of sub-basins within it, you could choose this option, and then obviously you need to have like a object ID, like a unique ID field in there, and that will just calculate the basin average PMP values for each one of the sub basins within the overall basin at the overall basin area size. So that's an option. And then we just have the option to include a depth duration chart in our output folder that we specified previously. It's just a simple PNG graphic of the PMP as it accumulates through time. And then lastly, we have the option to apply the temporal distributions. As we've seen earlier, there's a whole series of temporal distributions in there. If you choose this, the options of running all of the different durations go away, because for this tool to work, it needs to run all of the durations. So it will just automatically run all the durations for all different storm types and then apply these temporal distributions. And this will just output as a series of tables and basin averages. If you just have this, there's a couple more options that become available, and these do require the spatial analyst extension. So if that's not something that's available, you can still run the temporal distributions and you'll get a series of tables. But what these will do is they will take these temporal distribution tables and actually take the gridded outputs, and they'll, for each time step, we'll export a series of either ASCII files or then sum them all into netcdf files as well for import into any other software if needed. But like I said, they do require a spatial analyst, and it takes a little bit of time to run, but if that's needed, those are all there. And then after all that, we can just hit run, and if we go into view details, we can see kind of what's going on in here. We can see it's just creating our table with our, to store our PMP values, and then going through each storm and comparing all the rainfall for each storm and then to each grid point, and then whichever one is the largest becomes the storm that's governing PMP for that grid point for that duration. And it does that for every grid point in the domain, and just kind of loops through the process. So this is all there for reference. We can see what values being used from those DAD tables for each storm, and then it creates a series of raster files that's happening here, and then it will go through and apply our temporal distributions, which we'll see here in a second. And it's created a basin summary table here. It's choosing zone 4 and adding those temporal distributions for that zone. So like I said, that's all there. You can go back and reference and see exactly what's going on within that if you wanted to. I just canceled it there. It does take a little while to run. We'll go through that output here in a second and see what that looks like. So that was the PMP tool. So if we go look at what we just created, we can go back to our catalog view here. Go to folder, North Carolina. So that's when I canceled. So if we look at our output, I pre-ran this basin here. So what happened was it created a series of folders for each storm type. We have our general, our local, and our tropical. So if we go into one of those folders and look at our output, we see we chose to apply all the temporal distributions and then also create netcdf files and ASCII files. So we'll see we have one folder labeled ASCII, another one CSV, and then another netcdf, and then a geodatabase. We also have our PNG file that we talked about, that depth duration chart that we chose to output, which if we can look at that really quick, just a simple graphic. If you just really quickly want to look how the PMP was accumulating for the local storm there, that graphic's in there. Here's our folders. If we look in the ASCII folder, we can see we have each one of our temporal distributions. So this is the local PMP applied to each one of these different temporal distributions. If we just quickly look in one of them, we'll see a series of ASCII files for each time step. So we have, this is our 5-minute increments. So we have our 6-hour PMP distributed in 5-minute increments through all of 6 hours. And there's ASCII file for each one of those. And that's for each one of the temporal distributions is there. And that's for each storm type as well. We also have a CSV folder, and inside there, we're going to have our basin average values. So if you just wanted to look at real quickly, the local PMP for this basin as a basin average, we look at that, we can see we have our 1 hour through 24-hour PMP, and this is our local PMP for those durations in inches as a basin average. So it'd be average of all grid points that make up that basin. Then we have another one for our temporal distributions. Again, this is basin average values in 5-minute increments. So we can see here we have our 2-hour duration accumulating through time. And here I can pull this up too. So if we see, we have our 2-hour PMP is 18.57. Starts out, just incrementally increases all the way up to our full PMP for the 2 hours. We have that for here's our 2 hours, our 6-hour patterns, the critically stacked, 12-hour patterns, 24, critically stacked for the 24 as well. And we'll have that for each storm type. So We have our temporal distributions, and then we'll see a folder named, or a file named the same, but with a check under it. And what that's just doing is it's taking all of our temporal distributions, and then it's just comparing that to our standard PMP output and just making sure that the distributed values aren't exceeding PMP for any given duration. And we can see here, for the most part, they're pretty well. We can see a couple of them just exceed that a little bit. So that's something that you'd want to keep an eye on and explore a little further of why that's happening and if that pattern is appropriate to use in that instance. And then the same thing here, but this is just our controlling storm. So here we have our Huff patterns, and then we have the actual controlling storm. So these would be the storm that's controlling the 2 hour, and then also I guess these are in 60-minute and hourly increments. So this would be the storm that's controlling the 6 hour. You can see that here, the 6 hour controlling storm, and then the 24 hour controlling storm. So these are the actual accumulation patterns of those storms applied to the PMP. And then we have that same check file as well that compares those. So that's that. If we're going down the list, we have a net CDF. So here, the same thing as what we saw in the ASCII folder, where it's just these distributions applied to the PMP, just in a net CDF format. So if that's needed for input in the HMS or any other sort of software, these should be able to just be loaded directly in. Then we have a geo database here. If we look at that, the output we get, so this is back to the local storm. We can see we have a series of raster files, and this is a geodatabase Esri raster file. In the naming convention kind of goes over here. We have our local storm, and then our 2 hour duration, the name of the basin, and then the area size that the PMP was calculated for. So we can see we have that for each one of the durations run. We have that same basin average file that we looked at earlier. It's just here in the geodatabase as well. Then we have our PMP points that were calculated. So we can look at, here we have in raster format, we have that here in point format as well. So if you wanted to go in and look at specifically each grid point within the basin, you can see what that PMP value is at that grid point. You can see the controlling storm, and all that information is there. And then just our temporal distributions that we just looked at in CSV format are here in the geodatabase as well. So that's kind of the output of the PMP tool itself. So yeah, so we can run the PMP, that's output. As we mentioned earlier, there's another tool called the AEP tool. So look at that. And if we open that up, very similar to the PMP tool, we'll choose so we ran PMP for this Lake Julian basin, and now we're going to calculate the AEP for this tool. So again, we'll choose our input basin, Lake Julian. We'll choose our durations that we want to calculate. There's two options, one for the 6 hour, one for the 24 hour. Again, our output folder can be anywhere. We'll add that. So here is, you can run this tool without running PMP first, and it will just give you the return frequencies and the rainfall for each one of those return frequencies. But by default, this is checked, and this will just compare those to compare the PMP values to these as well. So obviously to do that, the tool needs to know what those PMP values are. So if this is checked, it'll ask you to find the output from our gridded PMP tool that we previously run. So what we'll do is, if we open that up, we'll go into our output we chose and our PMP that we just looked at. So we'll find it for the general storm and add our PMP points. And you can just do it to one, and it'll just look for the general PMP and do those comparisons. But if you wanted to compare them all, then just come in and we'll go back to our local points, add those as well. And let's just do it for tropical as well. So we have our point PMP values from that geodatabase that we looked at previously for our general storm, our local storm, and our tropical storm. We have our output and our durations and then our input basins. So if we hit run and then view the details, we can see that it's calculating our basin area size, and then it's going in and then it's finding our average basin average precip for each one of those return frequencies. So we have our 1 year, 2 year, and it'll show you what those values are. We have an upper bound and a lower bound, and then the average. We'll do one of those all the way out, and then it'll get our PMP values, and then we'll compare those, and we'll look at what that output looks here in a minute. So it did our 6 hour, now it's doing it for the 24 hour, same thing. This tool runs a lot quicker, so we'll just let it go through. It's almost done. PMP values, and there it's done. And you can save this if you want. Otherwise, we'll just close it out. Go in and look at what we just created. Output folder. So we can see it added. This is our PMP output that we created earlier. We can see we chose the same output for this AEP tool, and it added for each duration, it added an Excel file, and it added a PNG image. So if we look at those, we open up the 6 hour, we can see here's all our return frequencies, and then our basin average precip. So our basin average, and then our different confidence bounds. So we have our upper and our lower confidence bounds around that for each one of the return frequencies. That's there in Excel format. And then if we wanted a visual graphic of what that looks like with our PMP values, or where the PMP values actually fall in there, we can look at this image as well. We can see it calculates our PMP over here, the annual exceedance probabilities over here. It also plots them on a graph, so we can see our 6 hour general, local, and tropical PMP. So you can come over here and see, we have our 19 inches, 19.4 for our local PMP. We can see where that PMP value crosses our 6 hour precipitation, excuse me. And we have that for our 6 hour and 24 hour. And I guess that's about it. We go back. So there will be like we mentioned a little bit earlier, there's going to be a PDF file with documentation that kind of has information of running the tool, kind of the file structure, the output structure. So reference this as well with your first time running the tool, kind of walk you through the whole process. But it should be pretty straightforward. With that, I guess that's about it. Unless there's any questions we want to go over.
Yes, Jake. Yeah, thank you so much. This is awesome. It includes everything. So I have a couple of questions.
Sure.
The first one is when you have this temporal distribution and it says exceeds, what do we do with that? And the second one is when the area is calculated, what I saw was it rounds off to the next. Let's say if it's a 1.5 square mile, does it calculate for the 2 square mile? The result shows like 2 square. If it's less than 1, it says 0. This is what I have seen in the past. So can you explain those two things? Thank you.
Yes. Hey, first, thanks, Anush. First, on the temporal side, I'll explain that. So we have a number of different temporal patterns to use for each storm type for each location. And in general, our recommendation is to do the first cut with only ones that pass and do not exceed PMP at any interim durations, and evaluate if you have enough of them for each duration storm type to utilize. Now, if you look at those ones that say exceed, and they maybe only exceed by a very small percentage, 1 or 2%, for example, then we are generally okay with that. In fact, our guideline for the exceedance is if the exceedance isn't exceeding by more than 5%, then we are okay with using that because that's well within the range of uncertainty. But in this example that Jake is showing here, there's a couple of them that exceed, but Jake, go back to the table real quick.
Yep.
But we still have, let's just say out of the 12 patterns there, only 3 of them exceed. So we still have 9 patterns to use, and that's plenty. And those are all just a local storm type, right? But if your basin and you ran this showed that for the local storm type, maybe 10 out of the 12 exceeded, then you would want to take a closer look at that and see, hey, well, this one only exceeds by a couple percent at only the 6-hour duration. So you know what, we're okay with using that, for example. So that is the kind of delineation that you'll want to do. In most cases, you will have plenty of patterns that do not exceed interim PMP depths, and you'll have plenty to choose from. But in cases where you have a limited number left that don't exceed, you want to check that table and see if the exceedance is by less than, say, 5%. And if so, we're okay with using that. And Jake, did you want to add something to that?
No, that, I mean, yeah, for sure that. But like, I was just kind of doing a little exploring because I was like, well, why are these kind of exceeding? And that's kind of interesting too, is a lot of times it's the way our PMP is calculated. You know, we can see we're accumulating PMP, but then it kind of stalls out for a little bit and then doesn't accumulate for a couple durations. Whereas, you know, our distribution will keep accumulating. This distribution just keeps accumulating. So it does
envelope that. Yeah. And that's typical. I mean, that's the storms in the real world behave like that, where once they've accumulated their main rainfall, that accumulation shuts off until new storms take over. And so that's a reflection of trying to utilize observed data with idealized data, and that's what happens. But in most cases, you're going to have plenty of temporal patterns that pass. And again, if you don't, just check that table. And if they're not exceeding by more than 5%, we're fine with using that.
Yeah. And as far as the rounding goes, the tool does round off. If that becomes an issue, if we're dealing with really, really small basins, we can change that. But for the most part, like when you start talking about decimal points and square miles and stuff, it hasn't really been too much of an issue. So if you're noticing otherwise, it's definitely something we can take a look at and adjust.
Yeah, probably the PMP is being calculated considering that small area. But when the result comes, it says when I see on the Excel these results, it shows like if it was 1.5, it says 2 square mile.
Yeah, and a lot of that is like naming conventions, because we can't really put points and special characters in file names and stuff too, so it will just drop that off and round it.
But the calculation is done based on the correct area. So
there's down to 1 decimal point.
Okay. So if it was like 0.45, it's calculated as 0.5 square mile.
Yeah, we can look at that real quick. I believe here. Go back. Why isn't it letting me look at the history? Well, here, let's just. So we can see, it'll say, oh yeah. So yeah, our actual basin area size is 4.8. It rounds it up to 5 for the PMP analysis.
And so the calculation is based on the rounded off or on the actual?
Yeah, so it's rounding to 5, and then it's running PMP at the 5. But if you were to run it at 4.8 and 5, would you notice any difference? I don't think so, but if that's something we need to address, we can do that very easily. I don't know, Bill or
well, there wouldn't be any difference in the PMP depths. That would make no difference at all in the PMP depths. Yeah, so it doesn't make a difference for PMP.
Yeah, for this one, I think it won't be a big difference for 4.8 and 5, but sometimes we have like 0.27 square mile, 0.28 things. So it goes to the, in the result, it shows 0, but of course it's not 0. Maybe it's using 0.5. Is that correct?
You know, let me look at that a little bit more in depth. I'll dig through the code because I think it is calculating it out to 1 decimal point. It's just when it's just putting in some of these outputs, it's rounding it. I think for just naming conventions. But I will confirm that with you here in a minute. let me dig into the code late after the call here, and I'll let you know.
Okay. Just another question on the
Yeah,
temporal distribution. Yeah.
Because to do it less than 1 square mile, it has to do it down to 1 grid point, like you just mentioned there, or one decimal point.
So it's using 1 square mile for those areas less than 1 square mile.
Well, let me look into that and get back to you.
Okay.
I should know that.
Okay.
And Jake, I know you'll look at it and we'll confirm that, but the native resolution of the SPA's storm data in our DAD tables is 1/3 of a square mile. So it should be calculating anything less than that at that point value, basically. So, but we'll confirm that, Hadush, and make sure that that's in the documentation.
Okay. Yeah. Another question on the temporal distribution, just to fully understand. The 2 hour is the best fit for the local storm. The 2 hour is best fit. The 6 hour, 12 hour, 24 hour, others, they are kind of, there is 10 percentile, 90 percentile. Is that correct? That my understanding correct?
The 2 hour is based on an analysis of local storms where we have NextRad weather radar as part of the analysis. So we have a temporal and spatial distribution that goes down to 5-minute increments. So our temporal distribution for the 2 hour is based on actual 5-minute temporal patterns that we've observed in a series of local storms that are used for PMP. And so that's derived specifically from that process. And then the 6, 12, and 24 hour are, like you said, based on looking at those curves aggregated through those durations, and then looking at the 10th, 50th, 90th percentile, and so on. So the 2 hour is unique in the sense that it's actually taking observed 5-minute increments to develop the temporal pattern that's provided there. And then the 6, 12, and 24 are using more of the 10th, 50th, and 90th percentile processes.
Okay, thank you. And the 3, 4, 5 hours?
Well, those are just distributed following the curve shape and so on between and Jake, remind me, the 6 hour is that's still in 5-minute increments or 15-minute?
Yeah, local storm is all 5-minute,
5
and
minutes,
then
yeah.
general tropical are 15-minute, and
Yeah.
except for the controlling storms are all 1 hour.
Yeah. So Hadoop, using the 5-minute increments, you're able to obviously get 1, 2, 3, 4, 5, and so on, up to 6 hours or 12 or 24. And the curves.
Okay, thank you. Yeah. I think that's all from my side. Yeah.
Okay. Well, Jake, did you have anything else on the tool that you wanted to go over?
No, that's it from my side.
Okay. And Hadoop, obviously, this recording is meant to be able to help people walk through application and use of the tool and understand the inputs and outputs. But there's certainly still going to be questions. There's documentation behind this, but of course, we are available to answer questions or address situations where something doesn't happen. Jake, on your side, are there any issues that a user should be aware of regarding naming conventions and other of the fun intricacies that are related to ArcGIS and ArcPro and how those read files and cause crashes and so on?
Yeah. Just it's a lot of the standard Esri stuff. So special characters and naming conventions, spaces, OneDrive, like make sure everything's stored locally, make sure you have overwrite permissions on anything. And then like everything, Esri's software is very susceptible to schema locks. So if it's trying to overwrite something that was previously added to a project or something, that it will lock it up and won't let you overwrite. So sometimes you might need to close down the software or open it back up, or sometimes in extreme cases, maybe even restart your computer, but just kind of standard things like that.
Okay, great. And Hadoop, is there anything else on your end that you'd like to discuss after using the tool, and anything else before we finish the recording?
Yeah, for now, everything looks nice. Thank you. If I have further questions, I will come back after. I think later, as you said, there will be questions anyway later from me or from other people who are using this tool. Yeah, but I think this is a very comprehensive and it should be a very good, straightforward. To use this tool. Thank you.
Okay. All right. Well, thanks everybody. Thanks, Jake. Thanks, Adush.